In this video, we're going to be talking about cylindrical coordinates. So it's based off of polar coordinates, but the key thing here is that we need three axes. Cylindrical coordinates are in 3D space, so very similar to our 3D Cartesian coordinate system. But remember how we defined a point P, x, y in Cartesian coordinates, and it also could be represented by P of r phi in polar coordinates? Well, we're going to be using the same approach to discuss cylindrical coordinates so that we can understand where the name comes from. Then when you have a 3D shape, we can take advantage of cylindrical coordinates and find the volume, surface area. So we'll have to be able to find something called the differential length elements that will give us differential surface area or volume elements. So if this is confusing, then you might want to watch this video. If not, and you're already familiar with cylindrical coordinates and double integrals, then you could probably move on to the next one. But just as a quick overview of what we're going to go through first, in the cylindrical coordinate system, we're in 3D space. So that means we have something that looks like this. We have a point P over here, which is in 3D space. And we have our x, y, and z axes. But just like with polar coordinates, we want a different way of being able to represent the point P. So remember we had phi representing the azimuthal angle from x towards r. And now we just have to introduce an element or a variable that can raise the point to its specific height. So we introduce variable z that can bring us to point P after we've moved r an angle phi away from the x-axis, and then at that tip of r we can move z units up to arrive at P. Let's quickly go through an overview of the cylindrical coordinate system. So just to be brief, the cylindrical coordinate system is another way to represent point P, x, y, z in 3D space. We will use variables r, phi, and z. So I'm going to draw the diagram or the graph that I had before with x, y, and z, with this being the origin. Let's say we have a point P up here that's represented by x, y, z. It means that we've moved an x amount over, a y amount over, and then a z amount up. So this point P, if we were to use cylindrical coordinates, we know that it's going to be based off of polar coordinates. And with polar coordinates, we already have r and phi. So the only thing missing is z. So when we're looking at cylindrical coordinates, the first thing is that this point P is going to be a certain height z from the xy plane. Then we have a distance r that this point is away from the origin on the xy plane. And this r is at an angle phi to the x-axis. So now we have three variables, r, phi, and z, which we'll fill this in, with this being a right angle. And another way to represent P. So we can say this is P R phi Z. Is there a way to relate the Cartesian coordinate values to the cylindrical coordinate ones? Yes, there is. It's pretty much the same as your polar coordinate ones. You have y is equal to r sine phi, x is equal to r cos phi, tangent of phi is equal to y over x. You also have x squared plus y squared equals to r squared. The only thing left that we're missing is being able to compare z values. So I have z over in the Cartesian coordinates, and I also have z over in the cylindrical coordinates. So it's simply the same no matter which coordinate system you use. Z is equal to z. So when can we use this coordinate system? We can use it when there's symmetry about an axis. So as you can see with the diagram we just drew, you have your R. So just quickly do another sketch so I don't ruin the original one. You have a distance r that leads to a point away from the origin, and it's at an angle phi. With our polar coordinates, we know that if we spin r around 360 degrees, we're going to get some sort of disk shape. So that symmetry is going to be around the z-axis. So if we do have symmetry around the z-axis, then we can use the cylindrical coordinate system, especially if there's height involved. So if you were supposed to calculate the surface area or the volume of a cylinder, it would be easy to figure out the area of a disk first and then raise it up or down a specific change in height. So next, we want to look at some differential elements. Remember, we've done a few of these already. We need to be able to figure out what the differential length elements are in order to figure out how to calculate a differential surface area element or a differential volume element so that we can integrate and figure out the surface area or volume of a cylinder or something of a similar shape. So the first thing, looking at point P, we define several unit vectors. So we have R pointing radially outward. That means over here, let's try and find a different color. You have R pointing radially outward, R hat. What other unit vector would there be? We do have your phi So that means we're also going to have some sort of phi hat. That changes the angle R makes with the x-axis. And last but not least, we have z hat. To change the height. So from our knowledge of polar coordinates, we can start to figure out differential length elements. So let's look at the differential length elements. And keep in mind, there are three things that are going to change. We know that there's going to be dr, d phi, and dz. These are the properties or variables that will change. And in order to figure out the differential length elements, because some of these are going to be angles, we do have to sketch another diagram just to clarify what we're looking at. So I have x, y, and z. So essentially the question I'm asking is, when we take these baby steps, dr, d phi, and dz, what is the shape that we create? First, let's go with r. Trying to find a better way to do this. Let's say this is our first r over here. So that's r. And we're going to take this to be dr. Now we're going to start at phi, but at some point we're going to change the angle and we have d phi. So that means we now have a shape like this. From our knowledge of polar coordinates, we know that this is the arc length and is going to be r d phi. But that's just two variables. We need to introduce our third variable, and that means what happens if the height changes. So if the height changes, we now have dz. So that means there's going to be a height change for all of these. And now you can see there is some sort of 3D shape coming from this. And we have different surface areas that we can calculate, and of course a volume. So what are the differential length elements? We're simply just looking at the dimensions of this 3D object. We know there's going to be dr along r hat. We know there's going to be dz along z hat. And we know there's going to be r d phi along phi hat. So when we're trying to calculate the differential volume element, we're going to call this dV. If we're trying to find the volume of something, we're going to multiply length by width by height. And the differential length elements gives us exactly that. So we're going to multiply dr by dz by r d phi. That gives us dV is equal to r dr d phi dz. So this one's very important to know. So apart from this, we still haven't covered something, and I left it till the end just so that we can go through it in a bit more detail. We have differential surface area elements. And there's multiple ways of defining these because it depends on which surface you're looking at. So to sketch my 3D shape out again, have something like this. There's my 3D shape. I have dr, I have r d phi, and I have dz. So I want to be able to differentiate the different surfaces that are here. I'm going to use different colors. There's green, which is the top. There's going to be red for the sides, and then there's going to be blue for the curved surface. And we're going to call this A, B, and C. So the area of A is going to be equal to the two differential length elements that produce this area. So we know that it's bounded by dr and r d phi. So we have r dr d phi. That gives us an area made from the radial length and the arc length. We then have the area of B, which is given by dr times dz. And we have the area of C, which is given by dz times r d phi. So that would just be r d phi dz. Okay, so now we're able to do some calculations for surface area and volume. We're going to start with surface area, which means we have to pick which surface to calculate. So we're going to choose one of the differential surface elements we just wrote out. So let's calculate surface area. And this basically means calculating the surface area of a cylinder. So we know that ds is going to be equal to one of the differential surface area elements. If I want to calculate the surface area, there's something I'm missing. I haven't stated what surface area I'm calculating. I want to calculate the surface area of a cylinder, of the curved part of the cylinder. Now that we have a little bit more information, we can choose which of the differential surface area elements we want to use. So the curved part, as we can see from this diagram, has to be the blue part, C. So we're going to use ds is equal to r d phi dz. Okay, moving on. All we have to do is integrate in order to find the surface area, but we know that there are two variables, which means we need a double integral. But before we even set up our double integral, we need to know the boundaries. So find boundaries for for phi and z for a cylinder of length L our z values are going to go from 0 to L, and our phi values, there is symmetry around the z-axis, and we are spinning a full 360 degrees, so your phi is going to be from 0 to 2 pi for a full rotation. Now we can solve using double integrals. So we have the integral from surface area is equal to the integral from 0 to L and the integral from 0 to 2 pi, and we have r d phi dz. Before moving on, there is something that we should look at, and it's the value of r. It is a constant, but if we are trying to calculate the surface area, it isn't just any r. The surface area of the cylinder is going to be at a maximum distance away from the origin. So that means r must be capital R, the radius of the cylinder. So let's rewrite this, and we can also take out the r because it's a constant. It has nothing to do with phi or z. So we have r times the integral from 0 to L, integral from 0 to 2 pi, d phi dz. So looking at this, you'll probably go through a couple of tricks once you go through double integrals and triple integrals in your calculus courses. But when I look at the bounds, all of the bounds are constants. And that means it doesn't matter which order I integrate with respect to. So this is what we would call a separable equation. We can actually separate it into two integrals because so like this. So we can separate it into two single integrals as a neat trick. That means we have SA is equal to R this is simply L minus 0, and then we have 2 pi minus 0, and that is equal to 2 pi RL, and that gives us the surface area of a cylinder. So if we wanted to calculate the volume of a cylinder, we're going to use the differential volume element with bounds that are constants. Note that the differential volume element is dV equals to R dr d phi dz, just like we've covered before. So now I have 1, 2, 3 variables that are changing. It means I need a triple integral. But how about the order of integration? So I didn't want to explain why before, but we do have r dr. So we probably want to integrate that first within the bounds of 0 to capital R. So let's write this out. V is equal to the integral from 0 to L, 0 to 2 pi. And because we do have this r over here, we want to integrate that first. So it's going to be the innermost integral, and the radius is going to be from 0 to capital R, r dr d phi dz. So there are two ways to go about doing this. Number one, I can calculate this first, find the answer, solve for this, find the answer, and then solve for this. It's a lot of tedious work. There is a neat trick that we applied before where we separated everything, and why don't we do that again? Please note that you can't do it all the time. It's only when the function you're integrating, which is r, has an expression that can be separated into different variables. So this is a really neat trick that you can use. So note, if we have, let's say, integral a to b, c to d, just keep it, and then e to f, e to g of f of x, y, z, for example, dx, dy, dz, if f of x, y, z can be separated into individual terms of x, y, and z as products, such as f of x, y, and z is equal to, need more letters, h of x times L of y times m of z. So if we can rewrite our function as the product of three individual functions that are multiplied by each other, we can rewrite the integral and have a to b dz, c to d dy, and e to g of dx. So we can actually separate it into three single integrals. So in this case, we have the exact same thing. We know that our function is just r. And what about phi and z? Well, it's simply r times 1 times 1. So we can separate it. We can then have the integral from 0 to L with respect to z. We have the integral from 0 to 2 pi with respect to phi. And we have the integral from 0 to r of r dr. So that makes things really easy and a lot more convenient. We now have L minus 0 times 2 pi minus 0, and here we have r squared over 2 from 0 to r. So v is equal to 2 pi L capital R squared divided by 2 minus 0. V is equal to pi L R squared. So basically what looks very daunting, which is a triple integral, can be simplified if you first think through the problem and try to optimize your approach. The more practice you do, the faster you're going to get at recognizing these trends and patterns. There's one last coordinate system we haven't talked about, and that's spherical coordinates, and we're going to cover that in the next video.